that provide that bright color, that bright blue, shiny color. They're called iridophores. They reflect light using crystals made of the amino acid guanine. And you can see them here in this Tridacna gigas, what looks like little atolls there. Those are the eyes, and the light blue color around it is the iridophores. And speaking of eyes, some of the clams will have these, and now they're not eyes in the sense of the complex organs that we have, but they're very light sensitive, and they're scattered all over the surface of the mantle. On some species, they can even be elevated on little papillae like this. This is a Tridacna maxima. And on the edge of the mantle, these little spots are also light sensitive. And the purpose of that is simply to notice light and shadow. Giant clams, as is true with any clams, are delicious. So there are lots of predators that are trying to take a little nip of that big fleshy mantle. And having sensitivity to light gives a good advantage to be able to pull the tissue in and avoid being nipped at. So feeding and nutrition, a lot of the energy requirements of a tridacnid clam, most in fact, are supplied by the symbiotic zooxanthellae. And as I mentioned, they're located in these tubes connected to the digestive system, and they leak. The zooxanthellae are leaking the products of photosynthesis directly to the clam. Clams also do feed. They are filter feeders. They will take in bacteria, phytoplankton, zooplankton, as well as dissolved organic matter and even particulate matter. They'll eat it all. They're also, just like corals, they're able to directly absorb nutrients from the water right across their mantle. So they can assimilate inorganic nitrogen, ammonia, nitrate, and this benefits their zooxanthellae as well. I wanted to mention that in the history of the world, there have been other clams that grow to giant size. This one, Platyceramus platinus, you can look that up online. There's a lot of information about it. It occurred in the Cretaceous period. And it lived in anoxic mud and in water that had very low oxygen concentration, and it had symbiotic bacteria. So growing to a large size often is involving symbiotic or symbionts. But a very different type of symbiosis. It was not using light, it was using chemosymbiotic bacteria. So fascinating little subject. Let's see, how do they reproduce? Well, giant clams are hermaphrodites. They have male and female gonads. They start off as males, and as they grow, the larger clams are females. The mature clams can release either eggs or sperm, but they don't release them at the same time. The cue for spawning can be any number of physical or chemical cues, whether they're picking up the fact that another clam is spawning. It can be big swings in temperature, changes in salinity. A lot of things can stimulate a clam to spawn, and this can be somewhat dangerous in a captive situation because the release of the gametes into the water is quite a load, a biological load that can pollute the water. And the largest, the Tridacnus gigas, can release 500 million eggs in a single spawn. Let's look at some of the structure of a clam. This is the underside of Tridacna squamosa. Let's see. Just barely see that red dot right there. That's the hinge where the two shells are joined by a bit of organic matrix. This is the byssus opening, out of which byssus threads that attach the clam to the substrate may exit. These little scales on the side of the shell are referred to as scutes. The umbo is the union of the shell that right at a point, a triangular point there. There are some ridges here. There are teeth right here inside the byssus opening that are used for identification purposes. And then these scutes are located on ridges that are also important in the taxonomy. So let's look at the species now. Tridacna crocea is the smallest of the giant clam species, and it lives typically bored into Porites corals. It can occur in other corals, but its most typical location is very close to shore in the intertidal and bored into large heads of Porites. It has an extremely large byssus opening, but because it's bored in, it's pretty protected. Otherwise, there are a lot of predators that try to get at and kill a clam by nipping at the byssus opening. In the wild, the crocea clams typically have a fairly smooth shell with some little ridges on it because the scutes get worn away as it opens and closes inside its little pocket in the coral. However, when crocea clams are raised in an aquaculture situation, they're never allowed to bore into a coral, so they may have perfectly large and beautiful scutes. The distribution is right in the center of diversity for corals, and a little beyond. Right here. Well, in any case, you can see from the middle of the Great Barrier Reef all the way almost to Japan, not quite, and mainly Indonesia, Philippines. This is again from James' book. That's the underside there on the top, 2 clams. You can see how big a byssus opening for Tridacna crocea. And there's their typical appearance. Of course, there are many, many different color varieties. Solid colors too. And they have a very typical looking edge to the mantle. There, that spotting there. The Tridacna maxima can also have those spots, but they don't look exactly the same as in crocea. There's, when you look at enough of these clams, there are patterns that are typical. There are many of them, and then there's blends of different ways of looking at them. But it's like there are families of coloration schemes. And that's also Tridacna crocea. Does anybody remember that clam? That was the most unbelievable crocea I'd ever seen in my life. Was that at a MACNA? Was it IMAC? Yeah, this was a genetic anomaly. And photographs could not capture what that clam had. It was amazing. Okay. Tridacna maxima is the most common and widespread. And here we get to my opinion. I think it probably represents a group of closely related species that freely interbreed. It sometimes bores into coral like Tridacna crocea does, in which case it can be a little bit difficult to distinguish. In fact, some years ago I saw a shipment of clams from the Marshall Islands. And these were farm-raised clams. And there was one specimen of maxima, and crocea does not occur in the Marshall Islands. And this maxima had a huge byssus opening and a shell shape, rather compact and rounded, where if you were looking at the shell only, you wouldn't know that it was not crocea. The shell is a crocea, but the mantle was a maxima. And because of where it came from, it had to be maxima. So that just shows the far side of the range of what's possible for a pure maxima clam. There are also ones that look like squamosa. I'll show you at least one in here. And the patterns are very, very diverse. The patterns in the mantle. This again is from James, showing some of that variety of shape. As you can see, they're widespread. They cover the full range of the tridacnid clams. And sometimes they're fairly dense in population. This is one of Scott Michael's photos. In fact, there was a recent discovery of some very remote reefs where if there was a the clams, the Maxima clams were literally piled on top of each other, so that you look at this and you think, boy, that's a lot of clams, but at this remote site, if it looked like this, then somebody was overfishing. There are places where the shells of Maxima clams can build mounds of reefs, and you have live clams on top of it. Very interesting, phenomenon. I don't know if that was more widespread in the past or if that's just unique to a newly discovered area. Here's one that's clearly bored in and also being surrounded by, in this case, Acropora prolifera. That's a beautiful Maxima clam. And it's even possible for them to be pink in color, albeit rare. That's one of my favorites, the black and white zebra pattern. Sometimes orange with blue. Now the teardrop maximas have interested me. There was a study